Okay, so this video is going to cover the first two objectives of the first section of chapter 7. So I'm going to split this section into two separate videos. Objective 1 and 2 will be in the first video, and objective 3 and 4 will be in the second video. The only reason I'm doing that is because when you go to do the problems, you might need to rewatch the video. So instead of having to fast forward through the entire video, it might be a little bit easier if they're in the two separate videos so you can get to exactly the spot that you need without having to rewatch or try to fast forward through the entire video all at one time. Okay. I might recommend watching the entire video, both of them, then reading through the questions, and then maybe rewatching the videos so that it becomes a little bit clearer. I think as you're watching the video, you're going to find it straightforward, and then maybe as you go to do the questions, you might get a little confused. So again, you can just go back and rewatch. And so chapter 7 is all about the normal probability distribution. And 7.1 is called properties of the normal distribution. The one thing that you're going to have to keep in mind throughout this entire section and now for the rest of the year is any time that you're talking about a proportion, probability, or area, they all mean the same exact thing. So if you can find the proportion, you found the probability and you found the area. If you can find the probability, you can find the proportion and you can find the area. And vice versa, if you can find the area, then you've also found the proportion and the probability. Okay, all those words are interchangeable. So again, there's 4 objectives altogether. Objective 1, we're going to use the uniform probability distribution. And objective 2, we're going to graph a normal curve. Again, that will be in this video. And then the second video will be about stating the properties of the normal curve and explaining the role of area in a normal density function. So objective 1 is to use the uniform probability distribution. So let's look at this example. Suppose that the United Parcel Service is supposed to deliver a package to your front door and the arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. The delivery could be at 10 a.m., meaning that x is going to equal 0 if you were thinking about this as a graph, which you're going to see it as a graph on the next slide, or at 11 a.m., and in that case, x would equal 60. Why 60? Because there's a 1 hour interval there, and that would mean that each minute was 1 unit on your x-axis. So that's with all 1 minute intervals of times between 0 and 60 equally likely to occur. That is to say that your package is just as likely to arrive between 10:15 and 10:16 as it is to arrive between 10:40 and 10:41. The random variable x can be any value in the interval from 0 to 60. So that is 0 is less than or equal to x, which is less than or equal to 60. Because any two intervals of equal length between 0 and 60 inclusive are equally likely, the random variable x is said to follow the uniform probability distribution. So all things are equally likely to occur. So a probability density function, a PDF, is an equation that's used to compute probabilities of continuous random variables, and it has to satisfy 2 properties. The total area under the graph of the equation over all possible values of the random variable must equal 1. Okay, so the area must equal 1. There is no other option. Okay, and the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. Okay, and again, the reason that is, these are all going to end up being rectangles. Think about the area of a rectangle. Area equals length times width. So if you're talking about the height of the graph, it has to be greater than 0. Why? Because if it was 0, then it wouldn't exist. Your area would be 0. And if it was negative, your area would be negative, and you can't have a negative area. Just like you can't have a negative probability. So now let's take a look at what this graph looks like. Okay, the graph below illustrates the properties for the time example. Okay, so back to our Postal Service one. Okay, notice the area of the rectangle is 1, and the graph is greater than or equal to 0 for all values of x between 0 and 60 inclusive. So again, all I did was draw an xy axis here that I'm just highlighting in blue. And again, obviously that point would be the origin, 0, 0. Okay, and then up over here, again, we had x values between 0 and 60. So that's why, again, we went 0 to 60 there. So you're always going to look at that x side first. Okay, then we have to determine what the height of that rectangle is. So again, the area always has to equal 1. So the area is always length times width. And right now we know what the length of this rectangle is. It's 60. We're looking for the width, and the area must be 1. So to solve for the width then, if you divide both sides by 60, right there is the height of your rectangle. It's 1 over 60. Okay, very simply, do you need to go through this every single time that you're doing one of these problems? No. If this is 60, this is going to be 1 over 60. If your x value over here was 50, then your height would be 1 over 50. If your x value was 25, then your y value would be 1 over 25. It's just going to end up being reciprocals. Okay, so again, all this says right here is because the area of the rectangle is height times width, and the width of the rectangle is 60, the height must be 1 over 60, which is what I just explained when I was writing in the blue there. Okay, so values of the random variable x less than 0 or greater than 60 are impossible. Thus, the function value must be 0 for x less than 0 or greater than 60. Again, can't happen outside of that range, can't happen outside of that range. Okay, your package is being delivered between those two time frames. That's the only option. There's nothing above it, there's nothing below it. So the area under the graph of the density function over the interval represents the probability of observing a value of that random variable in the interval. So far what we've looked at is the entire interval, the 1 hour, and the area there is 1. Your probability that the package is going to be delivered in that time frame is 100%. But now let's take a look at this. Let's say that the probability of choosing a time that is between 15 and 30 minutes after the hour is the area under the uniform density function. So if I want to know the probability, that's what this question is really leading to here. I want to know the probability that it's getting delivered between 10:15 and 10:30. Hey, again, x is time. So in my graph, all I did was went to where x was 15 and x was 30. And now all I want to do is complete that rectangle. Again, that would be my length on the bottom, and then my width, and then we color it in. So that area of that rectangle would be the probability. Again, area, probability, proportion, all mean the same thing. So now if we're looking for the area of that blue rectangle I just drew, spoiler alert, it's kind of right there, but again, I'll go through it. Okay, again, I need area is going to be length times width. Okay, so again, the area here, the length here is 15. And your width, again, is going to have the same height as your original rectangle, which is 1 over 60. So you're going to have 15 times 1 over 60, or really 15 divided by 60. And when you do that, you're going to get an answer of 0.25, which means the area of that blue rectangle is going to be 0.25. But again, if the area is 0.25, that also means that your probability is 0.25. So there's a 25% chance that your package is getting delivered in that time frame, which again makes sense because 15 minutes represents a quarter of an hour. And there's your quarter of an hour right there. Okay. So it is 10 a.m. There is a 20% probability that the package will be delivered to your front door within the next how many minutes? So again, spoiler alert, the answer is right here, but I'm going to go through it again. Okay, so it's 10 a.m. So I'm starting at my start time. Again, remember that start time is 10 a.m. or x equals 0. And over here was 11 a.m. or x equals 60. So we're starting at 10 a.m. So again, there's a 20% probability. Probability and area, again, mean the same exact thing. So again, area is length times width. The probability is 20%. That means your area is 0.2 or 0.20 if you want to look at it as a whole number there. Okay, and again, we need to know our length and our width now. Okay, so again, we're looking for the number of minutes. So the number of minutes is your x value. We can call that the length if you want to be consistent. So I'll call that x. And again, we know the width of that rectangle already is 1 over 60. So I have 0.2 equals x times 1 over 60. And then all we have to do is solve this. To solve this, again, all we're doing is the opposite of multiplying by 1 over 60. You can multiply by the reciprocal, which is 60 over 1, or just 60. So you're multiplying both sides by 60. And when you multiply 60 times 0.2, you're going to get an answer of 12. So x equals 12. So in the next 12 minutes, there is a 20% chance that your package is going to get delivered. So our second objective is to graph a normal curve. Relative frequency histograms that are symmetric and bell-shaped are said to have the shape of a normal curve. Again, we've spoken about that prior to this section. If a continuous random variable is normally distributed or has a normal probability distribution, then a relative frequency histogram of the random variable has the shape of a normal curve. Again, it's bell-shaped and symmetric. And pretty much the picture that you're looking at, you've seen before. The only new vocabulary on there is you have two things called an inflection point. An inflection point is just the point of the curve at which a change in the direction of the curvature occurs. There's a mathematical way to find it. You don't really need to know it. You just need to know that right here and right here are the inflection points, which happen at the mean plus 1 standard deviation and the mean minus 1 standard deviation. That's the only thing that you need to know about it. Okay, and what's going to happen here is that if you increase the mean, that is going to cause your graph to shift horizontally, but it's going to maintain its shape. Okay, so again, if you look at the picture for the pink to the blue, your mean was 0, your standard deviation was 1. So again, if you increase your mean, I just randomly picked out 3, but kept that standard deviation the same, notice that it shifted to the right. So it's going to shift horizontally. Okay, and vice versa in the graph underneath, if you start with your mean of 0 and your standard deviation of 1, and this time I keep my mean the same, but I change my standard deviation, now look what happens to the graph. Okay, increasing the standard deviation causes the graph to become flatter and more spread out, but it maintains its location at the center. Okay, so that center is still going to be the mean there of 0, and again, changing that mean is going to shift that center to the right. So that finishes objective 2. So again, the next video will cover objective 3 and objective 4.